Hello and welcome to the day after tomorrow. We're Team Nicholas and we're going to be your hosts for the next 15 minutes. This is our team on the left, and we've divided our tasks into three groups. We have the explorers, the storm chasers, and the wind seekers. Looking at the background of the problem, most of the contiguous United States is at risk of hurricanes, as you can see in the image. Now, the number of weather and climate disasters in the US in the past 3 years, with losses exceeding 1 billion each, are 60, and all of these amounted to $2.6 trillion in damages from 1980. Now, that's a lot of money, and we could do a lot about it. And it's also a lot of lives, which are more important. When we have a quick look at the images, you can clearly detect the wind speed, at least in approximate range, by eyeballing the figures. The more circular it is and the more white intensity there is in the image, the faster it is. And this is a pattern we hope to exploit through our models. This brings us right into our problem statement. The job is to predict 3 missing images and to predict wind speeds for 10 existing images and 3 of our predictions. So that's what we're going to look into right now. Let's look at the losses and metrics we used to really get this up and running. Task 2 is super easy. We had mean square error. So that was a super simple decision for us to make because it's the most widely used metric for this type of applications, and it gives a very good result. Task 1, however, was a little more complicated. We found so many different indexes available online, and some of them sounded really impressive. But when we started using them and integrating them into our codes, the thing we realized was that even though they might be good mathematical models, when we look at an image and say it's a good model or it's a bad image, it's very different from what the metric says. So what we think is good could be said bad by the metric. And then we looked at SSIM, we came across this and we were like, hey, it's very similar to what we think. And so we decided to use this because on the images generated as well, it would have a good index on how similar they look. So the explorers, let's get into what they've been doing. We've done 2 separate things. We've done individual storm inferences and inferences of all of the storms grouped together. And the 2 images on the left are all of them together. The first one is a box plot of wind speeds, and that confirms a particular trend we had a suspicion all along. Most of the images have wind speeds around 40, 50, slightly higher than usual, but nothing to be alarmed about. And then there's, of course, that whisker at the top with a lot of high wind speeds, and those are the turbulent days, the actual hurricane days. The second image, the middle one, is about the number of images in each storm. We just wanted to have an idea about the number of images we're dealing with in our model. And the third one is about each individual wind speed. Again, we had a suspicion that most images were about a hurricane rising in intensity and then waning away. And so these images confirm it. They quickly rise, stabilize for a while, and then drop again. And that's what this is about. So let's get on to the job of the storm chasers. It starts with the data loader of the code. So as is with any image data loader, we downsized it and made sure that it's in grayscale, normalized it, and converted it into a tensor. We also ordered the images based on time so that we have a chronological sequence. When it comes to the architecture, we first perform a CNN on the image data and then pass it to the convolutional LSTM. Now, this LSTM output is passed to a transposed convolution layer, and that is the gist of the entire model. We'll look into the details in just a second. The training involves an SSIM criterion, as mentioned earlier. We used an Adam optimizer, and the number of epochs was 100 for the storm dataset. The synthesis is that the inputs are a sequence of images, and the output is a new image. So this is the entire model architecture, but the main point we should get out of this is that there's a convolution layer, followed by a convolution LSTM, followed by a transposed convolutional layer. That's the idea of the entire thing. So we use just one model in the beginning, and as expected, the first image that it generates is crisp and really, really good. But then the second image, that's still acceptable by most standards. But the third image, I think most of us had the collective opinion that, hey, we can't push this into production. So we came up with a new solution because no matter how much we tinkered with the parameters, we couldn't get any better. So here's our solution instead, with the knowledge of the fact that we need to generate 3 images for the task. We came up with 2 submodels using the exact same architecture we've seen earlier. The first one takes 5 images to predict the 6th image. The second model takes 5 images to predict the 7th image. So it just leaves one image and goes to the next one, the second time frame. Now, the advantage with this is that we can first create the first image using model 1, but when it comes to model 2, and we try to create the second image, we get a crisp second image. Using this knowledge of model 1's image, we can use model 2 again to get model 3. This way we have 2 excellent quality images and 1 almost excellent quality image, which is much better than 1 really good one, 1 average, and 1 bad image. Now, we could have trained the third model as well to just look at the 5 and predict the third one, but that was a bit of an overstretch, and this gave us good enough results because we were confident of our second image. So it saved a lot of training time by doing this. Let's look at the evolution of the model over the week. So all the images generated have always been 366 by 366. We thought about playing around with the image size, but we didn't get around to it. We were more focused on this innovative submodel system that we had. So the first one you can see is a CNN plus LSTM, the most basic form we came up with. And yeah, the results also speak for itself. It's not that good, and we couldn't present this. I mean, I could call it whatever I want, that image. The second one looks more like a hurricane, and it's a CNN and convolution LSTM, but it's much less complex than the final version we had. The third one is our latest and greatest model with that combination we just explained, the submodels, and that really looks good. We're really proud of what we came up with here. Now, we did look at other approaches as well, especially earlier in the week, and we tried to use these, but couldn't really get around to the final solution with these. So the first one was, because we're training on one storm dataset, we decided for this approach particularly that we could just create a model that takes the time as an input and generates an image. Now, the idea behind this is that you take an image and you take only the time factor and push it through the LSTM, and then try to deconvolve to generate an image and compare it with the original image metric. So the loss function evaluates the synthesized image with just the time and the actual image to get a metric and to backpropagate. But this didn't fully generate results like we wanted. It generated something, but we weren't really happy with it. And another approach we also tried was to use a GAN and LSTM combination as well. And these two are something we could have looked into further, maybe if we had more time, or maybe during our IRPs, or perhaps even a PhD, who knows? And the final thing we wanted to look into, if we had more time, was smoothing an image for consistency between generated images and ground truth images. This is more for task 2 people, because while they were getting really good results with actual images, when it came to synthesized images, the quality went down a little, and we thought if we smooth everything out, maybe the model trains to understand the generated images better. With that being said, I'm going to hand it out to the wind seekers.
Okay, now I'm going to introduce tasks to the wind seekers. So in total, we have tried 4 different models. I'll introduce it one by one. The first one we tried is just a simple convolutional model. As shown in this piece of code, it contains 2 convolutional layers and 2 linear layers, and it depends only on the input image features. Those images are reduced and normalized before they are passed to the regression model. This figure shows the simple CNN model's performance on a test set. As you can see, the model can predict wind speeds quite well when they are not changing very rapidly, but the accuracy falls at places where there are sudden changes in wind speed. Also, one problem about the model is that it relies highly on the quality of the generated images. So it can be an issue for future wind speed prediction. In addition, it cannot capture the trend of the wind speed quite well. So to solve that, we have integrated a LSTM model for time series analysis. We've used a pre-trained ResNet network to capture the patterns in the images and combine it with the time and form the whole input features before passing it to the LSTM model. The final output is generated by linear layer. But the model is too complicated because the pre-trained ResNet is quite complex, so it can take a very long time to train. So we have replaced the ResNet with a simpler CN model, but the model also did not produce results quite well that met our benchmarks. And the imbalance of weights of different input features was also a serious problem. So this is our final model. We pass the images to the CN model and pass the time features to the LSTM model. And finally, we combine them to form the input features and then pass them to a linear model to generate the final output. And this final model turned out to work quite well. This is the performance of our final model. We have retrained it on the surprise storm, and this picture illustrated its results on test set. As you can see, the prediction results is quite smooth, and it can capture the patterns in the changes of the wind speeds regarding to the time.
So now we'll get into the surprise storm TST predictions. So going into some of the outputs we got. So from task 1, the storm chasers looked at generating 3 images of storms based on the previous images we were provided with. So we can clearly see here that we have images of hurricanes just by eye. We can see a swirl pattern, and we can see they are quite similar given that they are quite close together in terms of relative time. And this was much better than the previous images we had initially. So if you remember that from this PowerPoint, we just had a bit of a blur to start with. So moving on to the wind seeker, so looking at the different wind speeds for the various relevant relative times. In these two tables, on the left column you've got the relative time, and on the right column you've got the wind speeds. So for the initial model results, we had a decrease in wind speed, but the results fluctuated quite a lot more than our final model results. So we can see there's a clear decreasing trend in the final model results on the right. And we found out that looking through our EDA, through the values we already had, that we were expecting a decrease in wind speed. So as might be expected with work like this, it's quite complex. So the few obstacles we came over, and we thought about 3 that were kind of key main areas we thought were most useful maybe to consider in the future. So we came up with logic initially for 2 models to create our 3 images, and that was specific for this task. So in future, we'd be thinking about maybe creating just 1 model and ideally create better results through that. And we also thought about using a transformer model, so utilizing attention through that. That was attempted, but given the time, we couldn't get that to work as well as the other results that seem to work very well. So we could also, as a third point, find more data. It would also be useful to have more compute units and further resource and time in this area as well. So you're probably wondering why you should hire us. So first of all, we are students. We're not charging a fee for this service, for this current models we already have. And for the next 9 months, we'd be considering, have to discuss, but we wouldn't really be too interested in charging for this service, for any support or research in that time. Number 2, we've clearly proven our ability to generate the models that work well for their specific tasks. So we've forecasted wind speeds and image patterns effectively within a very short time frame. And with a bit more time, we consider ourselves to be able to do a lot more. So we have explored these models so far, and we are eager to look at further models in the future. So thanks for listening.